This conference will now be recorded.
So the purpose of this webinar is to showcase the research done at Mirabilis Design on automotive avionics, particularly ISO, and then represent the solution in terms of injecting failures in the model or rectifying the failures once identified. So today we are going to discuss the brake model. We'll discuss about the functional safety and the standards about sort of types of failure, and we'll discuss some demo models on the same. Before we get started, let's talk about architecture exploration so that everyone of us are on the same page. The key term architecture exploration means that the specification that has been done on paper, PowerPoint, or Excel can be assembled and represent uh, like the model, as you can see on the right side, and then run variety of simulation by varying the speeds, changing the algorithms, arbitration, and evaluate the timing, latency, etc. to come up with an optimal solution. Now this is done for the following purposes: performance analysis, power measurement, functional correctness, and failure analysis. Performance analysis is related to time, for example, end-to-end delay, throughput, response time. Power measurement is more like related with the amount of power consumed per task or power per device, or even looking at spikes in terms of shocks. Failure failure analysis is about the analyzing the data and finding the cause of the failure. The functional correctness is about how to schedule your system. It can be at RTOS level, even at processor pipeline. So if you have any doubts, you can ask your question in the chat window. Okay, modeling an automotive system. So in this, we will talk about VisualSim automotive modeling. Um, okay, so in automotive system, one of the key area that we focus is on power consumption, because as well we move forward because if we move forward toward green energy, we move from combustion oil to battery, and battery need recharging. So architects very often want to reduce the power usage so that the recharge time cycle can be reduced. In VisualSim, we provide the user with power modeling tools embedded in the library, and you can model the system in a behavioral format where we can map the task to hardware resources. Um, VisualSim help the user calculate various metrics like resource utilization, response time, and buffer usage. Let me show you one of the example on power. Mhm. Yeah, over here. So in this, we have mappers, we have system resource, and we have the whole battery module. There's a power table and a battery. And if I run this model, we get to see the outputs. So as you can see over here, we have the battery charge. We have the battery life remaining percentage, and um, okay, and the time data plotter. So and then the display from the system resource. So so basically, by varying some of the parameter fields, we can see the variation at the output. And this is a very interesting plot over here, which says how the tasks are scheduled in the system resource. And as you can see, first the priority one task came, and then after some time we got the highest priority task over here. And and because of high priority tasks, only one time the low priority task uh, got into the system resource. So in VisualSim, we have the whole battery module, which can be used to see the power usage, and we can also provide the failure, which we will talk in the next slide. Okay. The next slide is about analysis and experiments. So in analysis and experiments, we will see that some of the architecture exploration that user wishes is as follow. Power consumption of an entire end-to-end system. Yeah. Power consumption of an entire end-to-end system. Analyze which unit or sensor is responsible for power spikes and shocks. Analyze the response time for non-critical application like ASIL-B application and for critical application like ASIL-D. And we have to check whether critical tasks were able to complete its task within certain time, and whether the response time are deterministic. We can have an algorithm and we can analyze its performance with different use case like increased load cases, etc. Functional safety is another area where architects focus more on nowadays. We have developed library for helping architects who wants to verify these constraints. Another area that VisualSim cover is helping user understand the heat and temperature profile of the system. Moving on, mobile auto energy consumption model. So in this model, we have a embedded system with sensors, with different types of sensors. We then have motors, vision camera, and IR. So when simulation runs, we keep checking on power consumption, and we look at power available whether power is available or not, and provide the commands. Now we see we have a lot of sensors, the embedded system over here, and in the next module, this is the model which I was talking about before prior development. As we move forward, we will be able to see the next power activity state. So in this slide, it represents the state diagram for power transitions in a typical automotive system. Let's say the vehicle is in parked state on no or very low power consumption, apart from few sensors like GPS sensor. When users start ignition, the power state moves to active. Before coming to parked state, it moves through an idle state. So if a battery charge falls below a certain threshold, it has to be recharged. So it moves to recharge state. So this is a flow diagram of the power state. The next slide demonstrate about the slide about the previous slides. So in this we have the state machine, and when the state machine is triggered, uh, it triggers the variety of sensors to do the work, which will generate the data sent to a buffer for processing, and then based on that it makes decision. Now what we are trying to show here is we can model the full system, and in that system there is a semiconductor, and we are looking at response time and power consumption, also at power consumption. So when changing manual to automatic or ideal state, you see how power usage uh, can be different, and and it shows a methodology of architecture exploration. If I go to the model, if I go to the model over here, we see there is a state machine over here, and in the behavioral model, computer, we have environment and model. And so the purpose of this model is trying to explore all the different use case that a particular system uh, is will go through, and they run different scenarios to see where it fails. So if I run this model, yeah, so we get to see the different process unit from different types of sensors and battery management and the plan, everything we get to see over here uh, in this plot. Okay. So if you have any questions, you can use the chat window, and we can answer your questions. So This slide shows a VisualSim power library component. As in the previous model, we already discussed about the battery module, so which is used for monitoring and managing system power consumption. We can say the parameter in the top right corner, as we discussed in the previous slide. By defining this parameter and linking this parameter with battery module definition, user can configure these modules very easily. So this slide show how a power okay the power table. So this slide shows how a power manager is filled up with details. We can see the different states, the device name, power states, OS, and state transitions. And we can see the different state which are column names. Yeah. And there is no limit on the number of state that VisualSim can handle. The frequency and voltage specification for device are mentioned here. So as you can see over that we have a scheduler unit 1 standby the its ideal state and the existing state and how much about the state transitions. Plots and analysis. These are the um, okay, the next slide tells about plots and analysis. Um, okay, so these are the list of analysis and plots which can be generated. We also generate GNU plots with much more color and detail from Power Manager. Okay. Yeah, plots and analysis. Uh, the next slide shows about the introduction to functional safety, and VisualSim support for functional safety. So before going in depth, we will discuss on what is functional safety. So it means that the automatic safety function will perform the intended functionality correctly on the system with on the system, or the system will fail in a predictable manner. So it helps determine the architecture constraint and also determines a product or system failure. Now in VisualSim, we already demoed the platform. So it is an electronic system level software for modeling and simulation of electronic systems, embedded software, and semiconductor. And it provides architecture exploration platform. And by running the model, we can uh, analyze the results and the reportings. For F.I.R and SOREP, we will be talking much more in depth about these two functionality in the upcoming slides. Standard overview. So as mentioned, IEC 61508, it is titled Functional Safety of Electrical and Electronic Safety Related System. And ISO comes under IEC standard. So it is an adaptation of IEC and applicable throughout the life cycle of all automotive electronics. Now, DO254 is about hardware, as you can see at the right side. And DO178 specifies the standards and specs about the software. Okay, this slide particularly maps the ASIL to different safety levels. Now, what is ASIL? It is a risk classification scheme defined by ISO for functional safety for road vehicle standard. So here the ASIL-D is dictates the highest integrity requirement on the product, and ASIL-A is the lowest. So as we can see, we have automotive, general, and aviation, and how everything is mapped to each other safety levels. So the ASIL are compared to SIL, risk reduction level defined in IEC, and the DAL, which is uh, design assurance level used in the context of DO 178 and 254, where DAL-A includes the greater hazards of large aircraft, and DAL-E is the with the lowest hazards. Moving on to sort of. So till now we discussed about the failures, about what so far that all the ASILs standard and ISO. So what is the SOTIF? So SOTIF was introduced in the ISO standard, and it is widely expected to become the first universal standard for highly autonomous vehicles. So how ISO and SOTIFs are related to each other? So far, ISO has been the primary standard in automotive deployment. That regulation focuses on functional safety, aiming to eliminate system malfunction. In the context of autonomous system, however, malfunction aren't the most important factor you need to worry about. So, SOTIF is more related to the unintended behavior which uh, can be generated due to the data received to the algorithm, and then they behave differently in extreme on or unforeseen situations, which cannot be predicted. So it's just like unpredictable failure that can occur uh, anytime. So that is why sort of is very important. Moving on, fault generation techniques. Here we will be looking at how we can generate faults in a virtual environment. These are two ways mainly. User can add them manually. We have failure injection blocks, which will inject failure automatically. And user can select the failure type from pull down menu, and then failure will be injected in the system. So let me show you the slide, sorry, the model for the network failure. So over here we have node blocks, which are used to send data from source to destination node. So suppose node 1 goes to node 3, and it goes to node 5, and similarly node 2 to node 4 and node 6. Here we have a network failure block, which if I double click on it, is having different types of failures, and all these failures are taken from the ISO standards, and we have implemented it in the VisualSim platform. So now if I run one of the failure, suppose I choose loss of communication here, which will detect the uh, if the packet come between the range, if the packet latency falls between the range or not. So if I commit it, we also have the input CSV file, which it will take data from. So this is the file, CSV file that the block will read. And for the first condition, we have my latency should fall into uh, one, 1 and 2 range. And for which block are we going to see this for node 5 and node 6? So here the user has to mention the block name. Now, if I run this model, I will get to see the result in the folder. So the network figure block actually generate the result in the it will create the new directory, and this is the file. As you can see, all the task source and the task destination packets will come. The status is the latency is out of range, at what latency, and the ID and for the block name. So this type of information will be presented in the failure network block. So suppose I take another model. This model, okay, okay, yes. So I'm talking about the now different model. Uh, you can see it in your screen soon. Okay, so yeah, we have a CRC block over here. VisualSim provide CRC error detection block. The traffic is used to send the packets, and we have behavior expressionist, which is used to manipulate the data structures. Now, for this, we have message corruption. And if I run this model, I will get to see where the mismatch of the data happened. So it will capture all the mismatch happening in the data in the CRC block. Now, the results will be generated again in the directory. Uh, as you can see over here, CRC gen, the name of the model and the faults. I double click on it and we get to see the text file. So we see that CRC checksum failed in what is the location of your block at what time. And we also get one of the value when it passed. So we also got that value as well. So all these failures and if it pass or fail will be detected by the network failure block. Now, if I run another failure over, suppose I run incorrect sequencing of messages, which tells about uh, so if you have any doubts, you can ask in the question. You can ask your question in the chat window. Okay. So I'm going to run for this model for another time for a different failure. I choose right now is incorrect sequencing of messages, which says that the order of the packet will be different. It will be like suppose the order has to be 1, 2, 3, 4, 5, 6. Then the order might change and it will be like 1, 2, 3, 4, 6, 5. Means 6 will come before 5. So if I will run this model, I get to see different latencies and between each packet and the delay. And if I see the destination node text display, I get to see, okay, let's see which. um, okay, as you can see over here, this is ID 18, this is ID 16, and I got ID 17 before ID 16. Before ID 16, of course. So this is these failures can occur, and we can see how our model will behave in those situations when the failure will occur. So for now, we only have some failures, but we implemented it, and we do have around 50 and 60 failures for particular failure block. So this is for network failure, particularly to inject the failure in the network block. Network model. We do have for software, hardware blocks. And if I show you the condition, and I run this incorrect sequencing of messages, which says it should fail at least 20% of time. So if I inject the failure, it will fail for 20% of time. And for the block, we don't need. We just want this out of sequence should happen for this fail percent. Yes. So moving on. To detection and diagnostic. So earlier we ran the model and we tried to inject the failure inside the model. Now we do have a block called diagnostic, and the it talks about if failures happened at any of the submodules or in any part of our design, we will capture those information immediately and it's written to the file. We also have a diagnostic block which monitor each and every blocks and record their status. So if packet are getting dropped or utilization goes about a certain limit, or if you want to check how many packets have a response time within a certain value sector, so all these things will be captured and reported back to the user. Okay. Moving on, we have a braking system. Uh, okay, so VisualSim model of a braking system. So in order to observe failure in autonomous driven cars and suggest solution to prevent the failures, we design a braking system module using a combination of different failures, hardware, software, network, power, and ATOS on a larger scale. Yeah. So, okay. So, yeah, as you can see in this slide, we have four wheels on the front and the back. We have engine, brake ECU, road condition sensor, specifically for SOTIF, the gyro, proximity sensors. So this model represents the miniature of a car braking system, which have all these basic details. And also we have a CAN ether switch, which is used to transfer the packets from one CAN network to another. So each packet is sent to the ECU via this switch and further processing. This is a brake ECU over here. So the task must be performed locally by each brake sensor processing and then the ECU for vehicle control. The RCS sensor, which is road condition sensor, used to detect the anomaly on the surface of the road. So if I run this model, I get to see. uh, So I'm running this model, and okay. So we get to see the brake latency from all the wheels, wheel 1, 2, 3, and 4. Uh, we get to see the utilization for that utilization percentage from the CPU, from the system resource. We do see the speeds, uh, which some points are there over here. And because of the execution time was a bit high, we got to see that my system resource was busy for most of the time. And the average power is also pretty high, as you can see over here. So if I and this message over here tells whether we are receiving correct data or not. So whether wheel 3 received the correct data at what time, wheel 4 received the correct data at what time, wheel 1 and 2. So this is specify whether we are getting the correct data from the ECU or not. All the wheels are getting the correct data or not. And this one over here specify the road condition sensor. This is a data is obtained from the road condition sensor. So this tells about the expected road state and the obtained road states. So as you can see, it can be like if the road is rough or it is smooth, and how the data is sent to the to the ECU, how it is processing. So we can see that what was expected versus what was obtained at the top. So okay. Now if I want to change the execution time to, and I run this model. So earlier my execution time was uh, vary, because for each wheel and each ECU sensors have given the various the variable execution time. Now I've fixed it with 2 milliseconds, and we get to see that okay, the utilization percentage from the system resource, we get to see the decrease in the percentage utilization of the resource. We and then we got more packets over here. The latency of the wheels got changed because we got more data packets returned. And as you can see, these two are main. We got to see that the average power also got decreased after uh, uh, some time. So that means with this execution time, the CPU got be much faster, and we got more packets. So this is how you can vary from the parameter you can vary and see the results obtained. And of course you can go inside all these modules and vary the individual one of them and see the changes. Okay. So uh, we showed these results, and moving on, this is okay. This is another use case for the braking system. And first it was the earlier one was having CAN network and different type of three CAN buses we were having, and the data was going from one CAN network to another via switch. Here we have a very simple module. We have again four wheels, and it is going through, everything is going to gateway, and from gateway it is going to ECU. And then we get to see, okay, from ECU it is sent back to the wheel and the other sensors. So as you can see on the right, we have a brake latency. For every wheel we have so this is like overlap. So we do have a latency for each wheel. The power, as you can see, is same. And then again the correct data read versus do we get the uh, wrong data versus correct data. Mm. VisualSim failure analysis. Okay, so here this is a very important concept for VisualSim. So this is a concept for failure analysis, and what is the FIR? So failure analysis is basically how the failures can be injected, and okay, yeah. So it is about when your design or your product fails, and the question arises, why does it happen? So failure analysis provide with information needed to express and correct the failure. Determining the root cause is very important aspect, because for that we need three steps. First is collection of data, and then analyze the collected data and determine the cause of the failure from the collected data after analyzing it. So to sum it up, in order to know the root cause of failure, we need to have a data and we need to determine with the corrective actions. Now, FIR here correspond to failure, identify, and resolve. So for this, mirror-based design provide a full end-to-end failure block, which I will discuss in the next slide. And I already discussed it in the previous slide about the network failure block and the diagnostic. So, and for identifying, we do have a diagnostic block, which will tell about the behavior of the model. And for resolving, we can use scripts where we can alter the algorithm, and then we can run it for different for different aspects. So now, if you can see in the right side, we have a model. The Here it is, first it is a running automobile. Then there's some failure occur. We report the failure. We recover from that failure, and then we go back to the top again. Functional safety using VisualSim. So far we discussed on the FIR concepts, or what is failure analysis, how Visual Sim is providing us with architecture exploration, where you can inject the failure, you can analyze the behavior of the model, if the model is running fine, and for some to see the different results. Sometimes we do have to inject the failures in real automotive systems. So then we have a block for this, and VisualSim uh, 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 a user can use VisualSim to analyze the results. Now it is for basically software, semiconductor, sensors, networks, and power system, where you can analyze your model in different, uh, ranges in different by altering the parameter values, by injecting the false, and see how it behaves. Now, moving on to the types of failures. So the types of failure, this slide will discuss different category, and all these is implemented in VisualSim, and how FIR concept has been used. Now, if we talk about hardware failure, it is related to, suppose if one of the core fail, and we see the system resource in the break model. So what if one of the system resource fails, so no package will go there to for the processing. So how it is going to impact your whole model, your whole system. Now, what if in software failure we discuss about data overwrites, which is the basic problem, the resource starvation, which is like what is the higher priority task uh, get the resource, and the lowest priority task wait for wait in the queue. So how can we can overcome all these failures? So for resource starvation, we do know that after some time we can increase the priority of the low priority task, and then it will also get the CPU, uh, the resource to execute. Now for a network failure, we have I already showed you all the failures in the network. That is, if the incorrect sequencing of messages, loss of link, what is the congestion occur in the network. For RTOS, we have if the execution time of the process is greater than the slot time. So then what will happen? What are the results which can be seen? For power failure, we have a processing, the slower processing speed, and then if the spikes are too high, and in terms of shocks, of course, then what all things can be seen from injecting all these failures. Now, now this is a sample report from VisualSim, the ISO sample report, which talk about the hardware failure and how in VisualSim are we implementing it. So suppose if a customer wants something very customized, they want to inject failure in the model and have the they have the specs. So yes, we can develop that block, and we can support that request. So this is a basic report from the VisualSim, and here we have DO254 versus DO178. So in the next slides, in the upcoming slides, we will talk about the latency, about the RTOS failure, about the software failure. So as you can see in DO254, we have talked about the RTOS failure, that is the real-time applications, which is very important. So that what happens, a timing violation occur, and then we need to shut down the CPU and restart it again after some time, which is very critical. And for DO178C correspond to software. So we have some data overrides value, well, like the incorrect data versus correct data. And at the lower bottom, you can see we have DAL A, B, C, and D, E, all the levels, and you can see which correspond to what. So suppose DAL B correspond to braking system. So we display the braking system, and braking system in automotive. But yeah, this is very important. So DAL is the like highest hazards that can cause a system to uh, malfunction. Now moving on, yeah, we talked about this slide sample. Okay, this is the sample DO254 report from VisualSim. Okay. So, DO254 in braking system, as I have already talked about, there was this one brake model with different, architecture. So in that, everything was going to the gateway. As you can see, the lower bottom, we have ECU. So all DO correspond to the real-time app, real-time fault. So we cannot tolerate the the task has to be complete within the real time. So issue means not timing violation cannot be occur. So all these types of failure can be seen in DO254. Subsection failure analysis. FIR table for brake system. So in this we will get to see some of the failures correspond to different hardware, software, network. So for suppose we already talked about the types of failure, and in that we see that hardware failure correspond to core fail, and inconsistent data correspond to software failure. So all these have been implemented in VisualSim, and when we move forward, I will show you one by one the models that has all these failures implemented uh, in them. So if we pass on, this is the list of power failures from ISO 26262 part section 5. Now, power spikes, battery life cycle, power overloading, heat generated, all these is implemented in VisualSim. And for now, I have shown you the battery life. I will show you the power spikes and the battery life cycle, and the heat generated and power overloading we already have discussed. Now, the power failure. So in this, we have a. Okay, let me go back to the model. Okay, so in this, we have already discussed this module. We have three traffic mapper, and everything is mapped to system resource. We have a battery module, and if I run this model, we get to see different, uh, stats, different results, and we get to see the change in the battery. Now, what is interesting is this over here. I have my aging factor, which is from random value between 1 and 6. And if I, so this corresponds to one of the failure, and how every time, like this one, about the battery life remaining percentage. So how it is falling over time. So you can see. So yes, this one is a very interesting plot. They showcase about how when injecting the failure, how it is, how the battery life is, how it is behaving. So this is one of the approach, and you can again change all these parameters, all these inside the expression list, and alter the value, and you can see the results. Okay. Going back to the slide. Okay. Moving on to the hardware failure. For hardware failure, we have core 5, and the failures like core 5 and unavailability of core 5, or any core, and whatever one of the core fail. So how we are going to identify it, and how we are going to resolve it. So if suppose one of the core fails, then we see that there is a sudden increase in the load to the remaining cores. Now, what can be done is we can eventually provide the request between the available cores. So whatever is whatever is remaining now can be used to send the request. Now, as you can see in the next slide, the hardware failure. So in this we have CPU cores. We have resource one. We have resource one, two, and three. Then we have traffic blocks and dynamic mapper, and everything is mapped to all the three resources. So now what happens is we get to see the change in the latency plots. Uh, okay. because of the network issues, you might be the slides might be lagging behind. Okay, so some network issue came up and you're not able to see my screen. So I'm just gonna continue with it. You all will get the, you can have the presentation later. So I will just give a brief intro of all the failures that VisualSim provide. So in the like we were talking about the hardware failure, and in hardware failure we talked about the loss of cores. So now, what is gonna happen is if one of the core will fail, we get to see that okay, the load is increased suddenly, and then we get to see that the available two cores are now have to are all the tasks are going to the available sources resources. So in the and then we talked about the software failure. In that, the inconsistent data, that is read data versus write data, and about the resource starvation. So all these, yeah. Um, okay, thanks, Tom. So yes, we have over here the software failure, and in this we have incorrect data packets and the correct data packets. We get to see that over time, at first we the read is happening to the memory, and then we get to see that okay, after that the write will happen. Write will go to the memory and change update the value. So then the next read will happen, then read will get the wrong value. So we will send the incorrect packet again, to the read, and okay, so we will send back the data packet again to the read, and then we will get the correct data value for the read. So in the bottom one, we can see that the Tom, can you move to the 42? We can see that there's a read data and the write data. After some time, we will get the correct read and write. Moving on to the network failure, we talked about the network congestions, the incorrect routing, the lot of loss of network connection. So then, yes, if we move on to the network failure slide, we do see that for this we are representing the congestion at node 2, because over time every flow 1 and flow 2, from node 1 and node 2 data is we are getting data from both the node, and at node 2 we can see the congestion. So over time what will happen is that there will be an increase in the latency. So you can see the plots. Moving on, for the RTOS, we have a model in VisualSim which represent uh, about the slot miss. So what happens is we have an execution time. The packet will execute for this much of time, and then we have a slot time. So sometimes due to anomaly, the packet execution time exceeds the slot time. So at that time, if this happened in a continuous flow, that so for after some time, what is gonna happen is slot is gonna be shut down, and then we will start the slot after the restart time. So restart time is one of the parameter. As you can see, yes, in this we have a slot time. We have three slots, which the values are 7 milliseconds and then 10 and 2. The thresholds is, as I was talking about, that after certain time, that is after a certain threshold, when the system will reach the threshold, the slot will be shut down, and it will restart after the restart time. So restart time is 50 milliseconds. So as you can see, the disable slot info. Uh, uh, Tom, can you move to the? Okay, so as you can see, the disable slot info will be printed on the command line, and if you can see the latency plot, there's a gap. Uh, as you can see in the slot 3, we got a lot of gaps between the packets. So that is when the slot exceeded the threshold reach, and the slot has to shut down completely. Now moving on about mirrorless design. So quick intro to mirrorless design. We have been around for 13 years, and we have built 250 product using library and infrastructure. Now, mirrorless design has the VisualSim software and large library modules, and we do provide training and services. Uh, and as we have, as I have talked about that, the custom blocks can also be made according to the request from the customers. Now, this is automotive library. We have a traffic, we have memory, storage, networking, FPGAs, and a lot of and all these libraries can be used to to develop, and it will help you to develop a model, and which you can analyze using the VisualSim architecture. Now, moving on. Yeah, so this slide is specifically the analysis was conducted as a part of feasibility report. The system under design was a large imaging system containing processor, ASICs, FPGAs, board, RTOS, and embedded software. Now, creating the same model in VisualSim help to eliminate to so it will eliminate the time uh, to about 1 month versus a development time which will take about 6 months using C code. So the increased analysis time and the ability to refine the architecture with the other team could reduce the number of error identified during implementation, and this was estimated to reduce the project development cycle by about 30 to 35 percentage. The increased efficiency and reduced development would drive early sales and produce increased profit. So, yes, so if you have any questions, you can ask in the chat window.